Welcome to Spring LIB.
Okay, in this problem we have X-rays being created in a cathode ray tube, and these X-rays are being created by electrons which are accelerated in the ray tube by a potential difference of 15 kilovolts, and are created. And we're ultimately interested in what's the minimum wavelength that these X-rays could possibly have. So this is a relatively simple problem. We only really need two small equations to find all the one quantity that we need, lambda. So we're going to assume that in order for lambda to be as small as possible, which is equivalent to the frequency of light being as big as possible, which is equivalent to energy being as big as possible, we're going to assume that these electrons, which are accelerated in this potential difference, gain the maximum possible energy and transfer all of this energy to the X-rays. So the energy of a charged particle being accelerated in a potential difference is just E times delta V, potential difference, where E is the charge of an electron in a cathode ray tube. These are electrons which are being accelerated. We also know that the energy of light is inversely proportional to its wavelength, lambda. The two constants that we'll need for this problem are the speed of light and Planck's constant, which I'm going to express in joules as opposed to electron volts. So let's jump into it. Okay, so using our first equation, we can figure out how much energy these electrons can maximally obtain through this potential difference, which is simply the charge times delta V. So the calculation is relatively straightforward. We can just simply use the electron charge, 1.6 e to the negative 19 Coulomb, multiplied by our 15 e to the 3 volts, E3 volts. And this will give us a result of 2.4 e to the negative 15 joules. And you can confirm that this number of joules is also equivalent to 15 kiloelectron volts. And I'll leave it up to you to determine why that is the case. Now, if we assume that all of this energy due to the accelerated electrons gets converted into the energy of the light, we can say that E is then also hc over lambda, which we can rearrange for lambda, which ends up just being hc over E. We can substitute in the E that we just solved for and use these values for H and C. I was a little sloppy, I left off my units. These are in joule seconds and meters per second. And it's over 2.4 e to the negative 15 joules, which will give us a resulting value of 8.28 e to the negative 11 meters. This is a very small lambda. So for context, this is about 1/10 of a nanometer, or 10 times, or 10. Let's just say it's a fraction, about 1/10 of a nanometer. That's good. So that's it. We found lambda. Thank you very much.